All right, so yes, hello everyone. As Professor Shelby introduced, I'm Aidan. I'm a summer undergraduate student, and we're going to be talking today about how to use customer-facing Wi-Fi data from the TTC to analyze subway performance in a few different areas and link that to user experience. We're also, this is sort of a work in progress, so we'll talk about some of the work that's yet to come on this. So I wanted to start first talking about why to use Wi-Fi data. And thanks to first BAI Communications for providing us with this data and making it possible for us to do this work. So we were motivated to do this work upon looking at some of the benefits and opportunities that the Wi-Fi data can provide to analyze the performance of the TTC system and see what given users' experience of the system is. So some of the benefits are a deeper understanding of the system. Rather than just seeing general operational metrics or tracking trains, we're receiving hundreds of thousands of user trips per day from across the system at all times. And these are full trips in many cases with origins, destinations, waiting times, transfer times. And so it's a rich set of data in that manner. These also, they're not recorded by tracking trains, but by tracking devices instead to represent users, which is after all who the transit system is serving. So it's rather than sort of using trains or other vehicles as a proxy to track how people move, it's actually just looking at how the people are moving themselves. And with such a large volume of data, it's easier to look at larger scale and system-wide trends that couldn't really be achieved by passenger counts or train operation data. And so the ease of acquiring the volume of data is sort of remarkable compared to other methods. And then finally, the data covers the entire subway operation rather than focusing on solely in peak hours. So we'll compare a little bit later on some peak and non-peak hours. So we're looking at not just seeing what the traditional peak performance is. So let's look at a sample journey here to see how the data collection process works. So once a user has connected to the TT Connect network, their device automatically logs the journey with the Wi-Fi access points, even if they didn't actively connect to the network on that given trip. So a device enters a station with the user and connects to the access point at their origin station at the concourse level. The user might pay a fare and then go down to the platform level, where the device would then connect to the platform access point. Once the train arrives and the user's device disconnects as the train leaves the station. As the train arrives at the next station, it will reconnect to the platform access point before disconnecting again as the train leaves that station. So this repeats until the user exits the train, connects to the platform access point at their destination, and finally would disconnect from the Wi-Fi network upon exiting the station, whereupon the journey would sort of be marked as complete in the database. So a journey is assembled from these connection and disconnection records on the same device. There's some logic kind of behind the scenes that BAI Communications does that it looks at assembling them into journeys, but it classifies the time that the user spent in the system as connecting between the origin connection and final disconnection as waiting time, running time, transfer time, or unclassified time in some cases, and it includes the origin and destination records as well. So for journeys with transfers, the same process applies, but the device is also recorded during the waiting and transfer time at the interchange station. Of course, over so many records, there's inevitably some data cleaning needed and some outlier trips. Some of the most common issues include the device not connecting necessarily at the origin station, or it might disconnect before the destination station, meaning that the true trip that the user took is not accurately recorded. As such, in this example trip, if the user was traveling from North York Center to Wellesley, if the device didn't actually connect at until York Mills, that trip would have been recorded as York Mills to Wellesley, and that can occasionally happen. Of course, we don't necessarily know what the intention of the user is, so it's hard for us to know exactly that, but we do have some ways that we've tried to reduce that. Sometimes as well, a device won't connect at intermediate stations when the train stops, meaning that we don't get waiting times, although we can generally infer a device would pass through. And some devices simply take longer to connect or disconnect. So it's kind of, for short periods of time, like waiting on a platform, it's not always accurate to compare device to device.
All right, so, as Aidan mentioned, this is a very sort of new and interesting and novel data source. So there's a number of things that we've been exploring over the course of, I suppose, a year looking at this. And I wanted to talk a little bit about some work done by an undergraduate thesis from Natalie Chu, which was excellent. So one of the first things that we tried was to see if there was a way that we could use, this arrival of devices at a platform and disappearance of devices to learn a little bit, like detect when a train had arrived and when a train had departed. And from that, get a little bit of a sense of when trains were actually arriving and departing at a station, because that is sometimes hard to get from the data currently available for the TTC. We tried a couple of different methods. The one you see visualized here is to simply just count the net number of devices you see on a platform. So as people arrive on the platform and show up and connect to the access point, the number goes up. And then as they presumably board a train and then leave the platform, the numbers goes down. And here you see sort of how that looks over time at Union Station. And then we can sort of look and say, can we use these peaks as a potential sort of detection point saying that there's a train here? So a bunch of people got on the train and left as well. There's another method which I don't have a visual for about trying to cluster trips together, again, based on when they are all sort of arriving or existing on the platform. Shout out to Yusuf for his help on that one as well. And you can see that we had mixed success with how accurate and how comprehensive we could the detection methods were. So at the bottom here, you just see a table showing some dwell time stats from the grouping and the peak methods, the two different methods we tried. The key sort of thing that we're still working on and hoping to maybe improve, if we can, is this difference between the number of trains that get detected in the two different methods, as well as the number of trains that are at least advertised by the static schedule. The differences may be explained by the errors in the detection method. They also may be explained that maybe the GTFS there's more or fewer trains running than what the GTFS advertises. So more work to be done there. Next slide. With some of this initial headway detection, we can start, or train detection, we can start to learn a little bit about the headways between trains and how they are in reality versus, obviously they're scheduled to be very even, but how they end up running in reality. So here's a few days of data showing the standard deviation of the headways at different stations along the line. And this is westbound, so it's running from left from Coxwell over towards Islington. And I like this chart because it shows both that there's variability between days, but also that there's sort of this general trend that as you go further down the line, more randomness gets added to the system. And so you see this increasing, general upward trend of headway standard deviation, which matches our understanding a little bit about the stochasticity of these kinds of systems. Next. And then we can translate this into also seeing sort of on a larger scale how the expected headway also grows as the randomness grows as well over time. Again, the index here on the x-axis is sort of the number of stations traveled. And so we can see this, again, general upward trend happening as trains run further and further along the line. Next. And finally, we are also exploring the idea of looking at major disruption. So here's a couple of great examples of a disruption that was reported by the TTC via their Twitter account. And we can see the results in the wait times experienced by the devices for those exact stations at those exact times. There's a huge jump. So, no service between Ossington and Broadview. We can see that there is a big jump in disruption and waiting time around Broadview, Castle Frank, and then we can also see the same thing over at Ossington. So there are a number of possibilities there to explore how disruptions affect passenger behavior as well. Next. And finally, there's some more simple metrics we can do. We can look at how long a device spends time on the platform, for example. So when do they show up at the platform versus disappearing, presumably on a train, if they're catching a train. And from that, we can learn a little bit about how long on average they wait. So the top chart is showing for line 2, the average wait time in minutes, sort of calculated over a peak period on a given day, and sort of the variability between stations. And then also the standard deviation, so how much variance there is in the wait time and which stations are more or less random and see more or less randomness. Next.
Perfect. So I'm going to jump back in here. So we then move to look at kind of journey time reliability analysis, and I'll briefly explain how these graphs are produced. So what we did here is we aggregated individual trips into station pairs. So for example, all trips from Jane to St. George during the AM rush, defined as 7 to 9 AM on weekdays, would have their mean and standard deviation calculated from all of those trips. And then the coefficient of variation for that station pair is one data point for the density graphs on here. So each station pair's coefficient of variation represented here is calculated from a lot of user trips within that, but is ultimately just one data point on these density graphs. So trips are then classified according to the number of stations traversed and the number of transfers. A short trip is 4 to 8 stations, medium is 9 to 15, a long trip is 16 stations or more. We excluded anything below 4 just because they're often trip fragments and they're extremely variable, so it's hard for us to know. The top graph is calculated using Wi-Fi data, and the bottom is from a GTFS feed. Clearly, the GTFS feed has much lower coefficient of variation, although we believe that the actual operational standard deviation is underestimated from this source. Regardless, it's easy to see that the graphs maintain a similar pattern between the route types. A shorter trip is always proportionally more variable, as are the ones with transfers, and it's most pronounced between a short and long trip, where the standard deviation for a given station pair relative to the mean travel time could be double or more, given that the coefficient of variation doubles. Yeah, so it's these data points are station pairs, not user trips. So this suggests that the user experience for some station pairs is quite inconsistent, actually, and a user would experience very different things depending on what trip they're making. So a user will experience a trip between a different station pair with a higher coefficient of variation. Their trip would be just much less predictable. And it suggests from this data that there must be a certain amount of base travel time variability that is heightened by a transfer. And this station, the standard deviation is just more pronounced relative to a short trip compared to a longer trip. So we know this from experience, right? If you're only traveling 5 stops, a 1-minute delay at a platform impacts your journey rather more than if you're traveling 25 stops, where that's just proportionally smaller. So it may seem like a fairly basic conclusion that shorter trips are more proportionally variable. The Wi-Fi data actually allows us to demonstrate this in a rigorous way that is a lot harder to do with other data sources. So we'll now take a look at the AM data compared to the data during our night classification period, which was 8 to 10 p.m. on weekdays. After the evening peaks, we really wanted to see how the system was operating outside of peak hours. It's clear to see a pretty pronounced rightward shift on the night data, suggesting that most station pairs have somewhat higher coefficient of variations outside of their peak hours. It suggests that some customers' trips are often actually significantly longer outside of peak hours, potentially due to disruptions, but the mean is not necessarily vastly increased. It's just less consistent. And this, makes sense if you're running at lower headways. Some people will still have a very short wait for the train, but some people might have a rather longer wait, and that affects the standard deviation a lot more than it does the mean. The data supports the knowledge that trains also may go out of service, crew may switch, and other delay factors that occur more often outside of peak hours, given that the system is not necessarily running at capacity. So we also are looking at the buffer time index. It's a metric for essentially how much buffer time a user needs to schedule to arrive on time. It's another way of sort of quantifying the uncertainty of a journey. And when a journey is less predictable in its travel time, an on-time arrival means that an earlier departure is necessary to guarantee that, even if that sometimes leads to an early arrival. This graph, we'll briefly talk about it, illustrates the distribution of the buffer time indices, again, by station pair, given how long the journey is on the x-axis here. So the red side on the left of each graph is for those trips with no transfers, and blue is for trips with transfers. The main thing to note is generally the wider and or higher spread of trips with one transfer, indicating that, again, that transfer really negatively affects the predictability of a trip. But even still, we see a very pronounced increased predictability as trips get longer, meaning that less buffer time needs to be scheduled. Finally, when we'll wrap this up quickly, what else can this data do? So the things we're exploring right now are looking at the commuters sort of versus returners experience. This is a unique time as we recover from COVID to see how people are going back to the subway and how their user experience might be different from the frequent users. So how are looking at the same devices over a number of days or a month even, how are these people, quote, learning to go back to transit versus people that may have been using transit all along? Does their user experience differ? We're also looking at the performance and experience of transfers specifically, and then finally looking at routing choices for trips with multiple paths. So how are people choosing to use the system? Is it the most efficient way, or are people making their own choices that might not actually be as efficient of how to go through the system? So yeah, just some key points to finish, and we'll take any questions here. So service variability increases in non-peak hours, leading to a less consistent user experience. The Wi-Fi data does remain variable due to the way that devices connect and disconnect. There's just some variability in that, but the high volume of data points allows us to kind of build these profiles and look at the standard deviation between different folks without too much impact from any given device that has a different profile. So I believe that's all we have. If there's any questions, we can take those.
Okay, well, thanks a lot, Aidan and Willem. Very interesting indeed. I think there was one question, but Willem already replied to it in the chat.
Yeah, there was another question, but I think those will be answered by in some way by Diego and Feras in a minute here. So.
Okay, there's another question here. Can you forecast how delays will cascade across the network?
Yeah, that's a good question. That's something. Yeah, that's something. I mean, there's two ways to go about that. One is to use the data to get really accurate senses of the randomness and the movement of trains, especially during disruption, and then use that to simulate something later on. Stay tuned. Or perhaps we can look at specific historical incidents of delays and see how they might cascade across the network. Something else I think would be really interesting would be to look at when there's a disruption and there's a bus bridging or buses replace. You'll see devices disappear at a station and then they might reappear later on at another station further down where the end of the bus bridging is, and learning a little bit how those delays cascade would be interesting.
Mm-hmm. We have another question. Do you guys have any thoughts on why the wait time at Bloor and Young was high?
It may be the result of a bit of a data anomaly, but it is also the case, as we see, that transfers can get chaotic. Bloor Young is more complicated than St. George as a station, and so there may be both technical reasons why that's happening that we need to dig into, and there may be actual transfer experience issues as well, and so they may be compounding together.
Perfect. I think, yeah, this is a good segue into the presentation, which again is going to use Wi-Fi data to explore OD demand patterns and try to model those. So the presentation is going to be, again, presented by two individuals. Diego da Silva is a postdoctoral fellow in the Department of Civil and Mineral Engineering at U of T. And he's engaged in various projects that involve data analytics. And his co-presenter is Feras Elsaid, who's a PhD candidate in our department. And in his PhD thesis, Feras is working on the management of mobility hubs and rail networks using machine learning methods. So Diego, over to you.
Thank you very much, Professor. So let me share my screen. Can you hear me well?
Yep. Yes, we can. Yeah.
Okay. So thank you very much for the introduction. Today we will present the research we have been doing over the last few months to estimate origin destination matrix for the TTC subway system using Wi-Fi and AFC data. We want to start defining OD matrix and its importance in transport planning. So the OD matrix is a data structure that maps trips to each origin destination pair in a given region. So the matrix can represent trips for different purposes. For example, work trips or education trips, shopping trips or social trips, for example. In addition, we can generate an OD matrix for a time of the day or by mode. For example, bus, subway, automobile, peak, off-peak. And its primary application is to support engineers, urban planners, transit policymakers, researchers in understanding distributions and demand patterns, as well as to be the essential input to the trip assignment problem, which deals with distributing the demand on the network links and nodes so that we can estimate link volume or delays, for example. So generally, the data source for building the OD matrix are household surveys, and some recent works use AFC data. One of the most significant examples is the Transportation Tomorrow Survey, or TTS. The TTS is conducted every 5 years and is a large-scale survey to estimate patterns of origin and destination from household interviews. It encompasses multiple municipalities and is the primary source of OD demand matrices in the GTA. In this slide, we have a simplified representation of the TTS process. So this year, the survey, we have an online option, which is really good. However, despite the substantial effort and recognized credibility, the TTS has some disadvantages, such as weekday trips only, short trips underreported, like leisure trips. The frequency between surveys and, for example, is 5 years, which is a long time, and it also does not capture seasonal variations because it's a cross-sectional survey, and it happened only in the fall season. AFC has become one of the alternative sources for generating OD matrices, and many researchers have been exploring its use recently. However, AFC is dependent on the Feras system, which can be done only at origin or tap-on systems, or such as TTC, or in some cases at origin and destination or tap-off systems. The main limitations are the data availability, usually not real-time, so the lack of information about the path chosen by the user or the intermediate stations or bus stops, and many incomplete trips. Recently, many transport networks have offered free Wi-Fi service. These services have brought numerous benefits, such as analyzing passenger behavior, route choices, detailed travel information, high data availability and quality, and low latency. One disadvantage is that Wi-Fi data only captures a subset of trips. Moreover, not all trips are complete, which demands an effort in data engineering to deal with missing data. So we can see that Wi-Fi and AFC data complement each other. So the two sources present an opportunity to construct a node demand matrix. In the case of TTC, the AFC data provide Presto gate counts. On the other hand, Wi-Fi provides a detailed itinerary counts and information about the intermediate stations. Consequently, we can generate matrices for multiple time aggregations. So for example, daily aggregations, morning peak, evening peak, off peak. So in this slide, we outline the data collection of the Wi-Fi network. So routers and the subway stations capture the connection and disconnection of passenger's device. We call a complete trip when the passenger connects to the street level router at the station 1, so the timestamp 0, and disconnects at the street level router at station 2, so the timestamp 3. During the trip, the passenger will connect and disconnect multiple times until the final destination, as the Wi-Fi signal is not continuous in the TTC network. This is one of the reasons we have incomplete trips. An incomplete trip is the missing connection and disconnection record from the origin or intermediate station or destination station. Okay, so at this research stage, our main goal is to estimate the OD matrix for the subway system, and we divide it into 4 tasks. So the first one is data engineering. So we are dealing with missing data and data imputation. The task 2 is the estimate. We need to estimate the full OD matrix. The task 3 is the exploratory data analysis, or EDA, and the task 4 is validation, task validation of our method. Okay, the task of imputing data in incomplete trips, this is still in progress. So this is the work of Feras. So Feras is helping to define the model and to identify the patterns. And we found a set of methods in the literature, which we list in the slide. There are some of the candidates to be part of our data pipeline, but we are still deciding which one will be better in our data set. For didactic purposes, we show two situations to illustrate incomplete trips in the data set. So the first example where the origin has missing data, and in the second example, both origin and destination are missing. So our first approach to deal with these examples is to investigate the frequency and recence of the trips for the same user. So the method has proven effective for most trips and mainly for commute trips. Okay, the second task is the construction of the data pipeline to generate the OD demand matrix for the subway system. We start by extracting the raw data from the Wi-Fi database. Then we build a matrix that maps the distribution weights of each OD pair. So this mapping is fundamental as it forces the distribution of each origin to be preserved in the model iteration process. The AFC data complements the matrix by providing the entries and exit aggregations. Recall that in tap-on systems, we do not have information on intermediate stations, only the entry and exit totals for each station. Next, we use the doubly constrained growth factor model that performs repetitive loops to balance the matrix until the sum of the origins equals the destination. So this is the only constraint to converge the matrix. Okay, for this presentation, we generate some preliminary results. We analyzed the 5 business days in the month of September 2021, morning peak and complete trips only. Also, we made some simple comparisons with TTS 2016 morning peak. Okay, before we start explaining the results, I need to cover the similarity concept quickly. There are many similarity measures, and we chose cosine similarity to compare each station's demand distribution. I want you to focus your attention on the upper right corner of the slide. The cosine similarity measures the angle between two vectors. So if the cosine of the angle is close to 1 or the angle equals 0, we say they are very similar. We say the vectors are unrelated if the angle is close to 90 degrees or cosine equals 0. So the vectors, they are orthogonal. Although it is not our case, as we are not working in the negative space, if the vectors point in opposite directions, they are very dissimilar according to the cosine similarity definition. The main advantage of cosine similarity is that it is not affected by the length of the vector or the value of the OD pair. In addition, we can compare samples from the same or distinct distributions. Okay, so that being said, we've noticed that the Bathurst station has more similarities to neighboring stations. As you can see, Bathurst has a high cosine similarity comparing to Christie, for example. Okay, and we can see that Bathurst has a high similarity with Jane, Hyde Park, actually Keele, Dundas West, and Dufferin, and Ossington as well. Okay. In addition, we see a clear separation between the stations on the green line and the others, which suggests the formation of demand clusters. In our second example, Finch West Station is similar to Pioneer Village and Shepherd West demand distribution. And as pointed out in Bathurst charts, we notice that similar stations are separated by the axis that divides the yellow line demand distribution to the left and right of Union Station. So all the yellow bars in the chart, they are in the left side from Union. Okay, when comparing it with the TTS 2016, we notice that the matrix generated by the survey is more sparse than the one generated by our method. So TTS has 52% values equal to 0, while our matrix has 31%. This partially explains the rate of decay on the demand distribution curve. So in our method, it is much smoother, while in the TTS, it is more abrupt. In addition, a more sparse matrix tends to concentrate demand in a few stations, which also partially explains the concentration of 80% of Chris's trips in just 10 stations, with 25% of its demand concentrated in Dundas station, which challenges a little bit our expectation. As we can see, our model starts with 8% and has a longer tail compared to TTS model. Another point that caught our attention is that if we consider the vectors as a result of the same distribution, the correlation coefficient is closer to 0. If we use the similarity cosine, which does not have assumptions about the distribution, we notice that for Christie station, for example, the demand is weakly related. Although it is premature to make statements at this point, we have some relevant results to guide our intuition. Okay, so next steps is we are planning to estimate the transit system OD matrix based on APC and AFC and Wi-Fi data, whichever we have available. More data is better. Comparison between the TTS and the results of our method, and enrich the database with information on operation disruption, special events, and mapping user choices for demand forecasting. So these are our reference for now. And I would like to thank the AI and TTC for supporting us. So thank you very much.
Perfect. Well, thank you so much, Diego and Feras. I know he contributed to the presentation, but he seems to have some internet issues. Okay, very interesting work indeed. One question I have is, computational time. Those matrices tend to be pretty large. Well, for the subway system is probably not huge because maybe 79 by 79. But in terms of computational time, applying your method, because it's iterative procedure. So how fast is this? Can you comment on the computational time?
Yeah, well, in terms of computational or running time, is quite negligible because it's very fast. It's very fast. So the way that we are dealing with the matrix, of course, we are using a lot of optimization to store the data and to process the data. So the pipeline is very fast, and the growth factor model is fast to converge. So we need just a few iterations to balance the matrix. So in our case, we reach the convergence with only 5 iterations.
Very good. Okay, another question from Brendan. If there was public Wi-Fi on board buses, could the same methodology be used for the total network, total transit network?
Yes, so definitely. This is one of our expectations to extend our work. So we hope that if we have access to Wi-Fi data from the buses, to extend the method, and probably we can apply the same method for buses as well.
Perfect, very good. I would actually maybe also invite you to think, maybe Wi-Fi on buses is not going to be sometime soon. It's probably going to take some time, but we have APC data on buses. Could one at least, for example, estimate the feeder trips on surface transit going to subway stations and vice versa, by fusing both the Wi-Fi data and the APC data? I'm not necessarily, it's not a question, it's just a thought and a comment. So
yeah, definitely. I think the difficulty is when we connect more than one mode, actually we need to understand the interaction between these two modes. So probably it's a more complex model, of course, when we compare with a singular mode. But the main idea is to is to distribute the trips across multiple modes and geographical regions as well. So the idea is to replicate TTS, but in a reverse way. So instead of households to transit network systems, we start from transit network system towards households.
Yeah. Okay, well, thank you very much, both of you. Very interesting work indeed. Okay, so we shift our focus. Actually, we move across the globe to China. Jinyi Chen is a visiting PhD student at U of T. She's been with us for almost a year. She's originally from Southeast University, and in her PhD thesis, Jinyi is interested in the analysis and modeling of resilience and failure recovery of urban rail transit systems. And she's going to show some of her PhD work. Jinyi.
Good morning, everyone. Can you see my screen, Professor?
Yes, we can see it.
Okay, now I will start. I'm very happy to be here to introduce some situation about Nanjing Metro. And today my topic is disruption delays in Nanjing Urban Rail Transit Network, analysis of disruption duration and frequency. And I will introduce my research from these following 5 aspects. And first, I will give a brief introduction of Nanjing Metro Network. Then I will talk about the data preparation and the methodology. And for the third part and the fourth part, they are the delay duration, survival analysis, and delay frequency panel regression, respectively. And the last part is the conclusions. And Nanjing Metro has 10 lines, and the operating mileage is 378 kilometers, and the daily ridership is more than 3 million. And this network has 159 stations, including 13 transfer stations, as shown in the picture on the left. And some of the transfer stations have more than 100,000 transfers a day. And the data I used here is the monthly disruption event report of 2019 before COVID. And I also used the ridership and train schedules from March to June for the panel regression. And the disruption are classified into 4 categories based on their severity. And this table below shows the classification standard and the frequency of these 4 types of event. And among them, this type 1 event has the severest impact on the train operation, and it can cause more than 2 minutes delays. And this data have specific time and location and impact of the event. And from the data, we can get 4 categories of independent variables. They are spatial variables, temporal variables, rhythm variables, and degree of influence variables. And the dependent variables is delay time for this type 1 delay, and the event frequency for the type 2, 3, and 4. And for the delay duration, I built the survival analysis model, and I use the Kaplan-Meier method and log-rank test for the univariate regression, and use the Cox proportional hazard model for the multivariate regression. And this Cox regression assumes that the risks increases proportionally. And for the delay frequency panel regression, here I built 2 models. One is the fixed effect panel regression model, and another is the negative binomial panel regression model. And I use this archaic information criterion and Bayesian information criterion to evaluate the fitting goodness in order to prevent the overfitting of the model. And for the spatial distribution characteristics, these 2 pictures below show the survival function by line and survival function by station type, underground or above ground stations. And according to the log-rank test results, the line and whether it is an underground station have significant effect on the event duration. This means that there is significant difference on delay duration between lines and between underground and above ground stations. And for the temporal distribution characteristics, the 4 pictures show the survival function by some temporal variables. And from the results showed below, and none of them had a significant effect on the event duration. So these are the univariate regression. And then for the multivariate regression, here I use Cox proportional hazard model and selected 7 covariates and defined the event as whether the delay ends. And here 1 means the delay ends, is the event happens. As the result showed on the right, here the operating years and underground or not, and a number of trains affected passed the significant test. And this second column is the regression coefficient of the variables. And if this regression coefficient is bigger than 0, it means that this variable is a hazard factor. And when this variable increases, the hazard function value will increase. And the survival time, here is the delay duration, will decrease. And if this coefficient is less than 0, it means a protection factor. So when the variable increases, the delay duration will also increase. And for the delay frequency, here I built the panel regression models. The data here includes 13 weeks from March 4th to June 2019. And here I showed type 2 data as an example. Here the independent variable is the station weekly passenger flow and station weekly train number. The dependent variable is the weekly frequency of the station disruption. And the first model is the fixed effects panel regression model. And from this F-test result, we know that not all of the coefficient of the selected variables are there. It means that there are important explanatory variables among these selected variables, so they can be removed from the model. And for the second F-test result, it shows that not all UI equals to 0. So it means that this fixed effects model is better than the pooled model. And for the negative binomial panel regression model, the result is similar to the fixed effects model. And here we can see that the weekly passenger flow and weekly train number have passed the significant test. And here I use the AIC and BIC to evaluate the fitting goodness. And here this model 2 is better than model 1. And for the last page is the conclusions and future steps. Here for the delay duration, I get some conclusions is that the longer the operating years and the shorter the delay duration. It means the new lines may have longer delay durations than the old lines. And second is that the delay duration of the underground station is shorter than the above ground stations. The third is that the more trains affected, it will cause longer delay duration. And for the delay frequency, here are 2 conclusions. First one is that the more station weekly passenger flow, the less disruption frequency. I think this may be because that some remote stations may have less maintenance than the busier stations, so it will have more frequency of the disruption. And the more station weekly train number is the more disruption occurs. But here I only use the weekly data, and later I will use some data of everyday daily data. And for the future steps, first I will add some evaluation of this survival analysis result and try to apply accelerate feeder time models. And for the panel regression, here I only have two independent variables, and I will add more independent variables to this panel regression and use some more time. Maybe I will use the daily data. And that's all for today's report. Thank you for listening and welcome your suggestions.
Thank you very much, Jinyi. Very interesting indeed. So can you just clarify for type 1, which are the long delays? So what's the range of those delays? So you're saying it's everything above 2 minutes.
Yes, type 1 delay is recorded the specific delay duration time, but for type 2, 3, and 4, they are less than 2 minutes, so they are recorded as 0. And for type 1 delay, it may cause severe impact, and maybe some of the train will be removed from the timetable, or some train may change their route. So this type 1 have a severe impact on the train operation.
Yeah. Okay, and your choice of models for the negative binomial regression, what was the rationale for that? Like, is there similar problems that use this kind of model? And I was just trying to understand, yeah, the rationale behind using that kind of model.
Here, I choose a fixed effect model and negative binomial panel regression model is because that my delay frequency data is the panel data is very small, and this data is the discrete data, and in some paper they use this negative binomial panel regression to evaluate the frequency of maybe the collision or other types. So here I use it in the delay frequency.
Yeah, there's definitely a lot of similarity between the problem you're tackling and road collisions and the collision frequency models, which many of them, they use negative binomial regression models. And so, well, thank you very much. Very interesting indeed. Okay, now we shift back to railway simulation. So the last presentation is going to be by Willem Klumpenhouwer, who spoke earlier on. So I already introduced him. So Willem.
There we go. Thank you. Hopefully my screen's visible.
Yeah,
okay, great.
That's good.
Yeah, so I'm going to move from sort of this hands-on, data analytics thing to a bit more of a future forward project, shall we say. One of the nice things about these TAL days is that you get to see research happening at various stages, and this is sort of conceptual and proof of concept. I'm going to talk about a project I'm working on, funded by NSERC, and of course, as a postdoc here at TAL, building a simulation platform for urban railways, which I named such so that I could call it SPUR, which has a great railway connection. If you're a GitHub user, I will shout out that you should check out the Transit Analytics Lab GitHub page. This project's on there and is open as well. So the idea is I got into the idea of what I'm calling big picture railway modeling, with the principle of really wanting to get useful results, quick results, test really kind of weird ideas, outside the box ideas with minimal investment. So a lot of railway simulation is very microscopic, it's very detailed. Of course, that's very important for planning planning the railway corridor and doing the final measurements and stages. But there's definitely seems to be a gap, especially in the simulation world, of being able to quickly put together ideas without having to spend too much time or too much money or have too much railway knowledge in order to build them. And there's a number of different possible applications for this, many of which are trying new service planning or new corridor planning from a larger sense, modeling larger networks and looking for broader effects, doing things like delay propagation as well. So we're calling this a mesoscopic railway simulation platform compared to a microscopic one, which you may be familiar with, such as OpenTrack or RTC, where all of the train dynamics are modeled, and then versus maybe a macroscopic one, which usually uses just simple fundamental diagrams to sort of get a larger assignment model for railways in certain situations. So the idea here is to take the microscopic, keep the agent-based idea so we can keep track of trains and where they are and how they're doing, but abstract away the curves and the grades into a simple nodes and edges type network, change the control logic to be fairly simple, follow a few basic rules, again, change the train dynamics to be based on fundamental properties or as flexible as we need them to be. And then the idea here is that you can take this, the setup goes from needing to understand everything and know everything about a specific railway corridor to being able to get the fundamentals down and create things with minimal specific railway engineering knowledge. And also by abstracting, you get the chance to scale things up a little bit. So the hope is to be able to look at a regional or even national level type model and to be able to model these things quickly. To keep the running time as short as possible and maybe even incorporate some real-time updates to the model as they go as well. So the sort of 4 goals that we set for this or that I wanted to see out of this was to, again, to be able to quickly build models, to be able to add detail and flexibility where needed, again, because this is certainly going to be used as a research practice. We need to be able to take different aspects of it and add detail where it's needed to model very specific effects if needed. We want to keep track of individual vehicles. That was very important to be able to have sort of agent-based modeling. And then we wanted to be able to scale. So for that reason, there were sort of these 4 outcomes that I settled on in terms of design. So an event-based, a discrete event-based model runs quickly. An agent-based model lets you track vehicles. Modular lets you sort of add complexity, substitute in more complex components where needed. And then a graphical interface is something we're working on to make it usable for multiple people. Here's just sort of a brief structure of how the model is currently works and is currently set up. So there's a model controller. There sits on top of a network. So there is the ability to do routing, to do some shortest path routing, any sort of network graph type effects. And each portion of the network, so each edge of the network represents a component, and that component could be like a station platform section of track. It could be a single section of track between 2 signals. It could be a section of track that's 200 kilometers long and has multiple signals. So that it can be really abstracted to whatever needs to be. And then trains sit on top of those components, and trains will arrive and request use of that component. And then based on what's happening with the component, it will allow the train to move. It will tell the train how long it takes to move through that component, and then it'll release the train and the train can move on to the next thing. So trains follow a route. The route can be updated if needed during the simulation, but trains follow a route, but generally just ask to use a piece of infrastructure. The piece of infrastructure tells them how to use it. And so for that reason, we can change the complexity in different pieces of infrastructure very easily. And then all of this gets modeled so that we can monitored, so that we can keep track of how trains are moving around. One thing we also wanted to add, don't worry about the structure of this too much, but one thing we also wanted to be able to add was stochasticity. So being able to capture the fact that travel times between 2 points or on a given track or between 2 signals might be random. And so to do that, I'm leaning into my physics background and drawing from the sense of perturbations, which I'm calling jitter here for a little bit of a nicer word. But the idea is to be able to take a sort of static deterministic model and then perturb how travel happens between different components in different ways. It can follow a distribution. It could be pulled sampled directly from data. For example, if you had a big distribution of Wi-Fi data between two stations, you could use that as a distribution for how the train might move. And then you could use that to simulate other effects. You can add very specific effects as well. And so that's part of how the component behaves as well. So there's a stochasticity layer that sits on top. We also wanted to be able to make this relatively easy to set up. So, the example as a proof of concept we've been looking at is I've looked at line 4, which is the Yonge Sheppard subway line, runs from Yonge to Don Mills. 4 simple stations, the trains run back and forth. So the travel times between those stations, we grabbed straight from the GTFS static data. So we were able to look at how long it suggested the travel time should be between these stations. We can connect up these components into a network. So we simply have a fairly simple graph that's a straight line in 2 directions. It's a multi-directional graph, and trains can run between those stations. And so we're able to produce, originally able to basically produce the scheduled Mary diagrams or the scheduled string line diagrams showing trains moving throughout. And then just as an initial step, I added some jitter, some randomness in the data that would delay a train by a certain amount of time, just to throw a wrench into the network and see how the trains respond. So, we can see here at the top is a very simple bit of delay where a train is delayed roughly a headway. So the train behind it is kind of directly stacked behind that train. And so it does wait and it does follow the train. We don't have any problems with overlapping trains. And then if we delay the train significantly, say there's an accident or the train is delayed for several hours, the following trains also bunch up behind that and have to run consecutively, just simply based on the rules set by the components that they can only handle, say a section of track can only handle 1 train at a time. I'm also working on a graphical interface. This is very preliminary, a very preliminary idea, but partly to make it easy for myself to assemble these kinds of simulation ideas and situations together. But the idea will be you'll be able to click and drag components together, assemble them into a network, and then test how that runs based on various schedules or various operating principles as well. And finally, just to leave you with this picture, I wanted to sort of show the fact that you can scale up the complexity, or at least scale up the size of the network, or the size, the realism of the network, shall we say. This is an example of the Go subdivision, which runs for the last portion of the Lakeshore East line, so from just before Pickering to Oshawa. And this is all from the track diagrams that Go Transit uses. So we have each section, each signaled section, and each station is represented by an individual component of different types. The different colors represent different behaviors that can be coded in to those as well. But even now, as this is assembled, you can start to simulate train movements along there as well, and look at different routing components. So I will leave it there since lunch is coming up, and happy to answer any thoughts or questions. I can hear my stomach grumbling. So,
thanks, Willem. Very, very exciting indeed. As you mentioned at the beginning, rail simulation is a non-trivial task, especially with existing simulation packages. It's an enormous undertaking. So developing something that's relatively simple to develop and data-driven would be extremely useful. One question I have is, how are you dealing with dwell time at stations at this point?
Yeah. So station components have their own behavior. So, from the simplest point of view, a simple thing of track will say, we know it takes 45 seconds for the train to cross this section of track. The train enters it, and then I say the train waits for 45 seconds, and then it appears at the end of the track. So we can do the same thing with stations. So we could have a station component that can take more or less detailed information about, say, the demand. So we could have some understanding of the boarding and alighting demand. It could calculate a dwell time, like a static dwell time for starters, and say, okay, well, there's 20 people getting off, 30 people getting on. That should take, the doors open, the doors closed, that should take this long. And then if there's a need to add some randomness, we can also add that jitter on top of it. So stations are treated basically as another track component that the train can travel. The stations also allow, or any component really also allows you to set a scheduled departure time. So if a train is running early ahead of schedule, you can add in that holding where the train will wait and occupy that until it's ready to go as well. So by abstracting it, we can really kind of dream up any situation we might want.
It's definitely a very strong design feature to have this modules and components separate and can be modeled at different levels of complexity. I think there's one question that's probably related to what I asked. Feras is asking, I'm wondering how you are moving the train from one station to another.
Yeah.
Is it based on travel time only?
It is based on whatever the component decides it's based on. So all the train knows is it needs to go through this set of pieces of infrastructure. It has a list that it follows, and then the component decides based on what's going on around it and its sort of fundamental properties, how long that takes. So travel time is ultimately the train has to take a certain amount of time to traverse a certain section. How that's determined could be up to, again, demand if it's a station, could be up to, if you have a big long section of track, we could kind of have a congestion function or a fundamental diagram approach as well. So those travel times can be determined basically however we want. You could build in some physics if you needed to the train to speed up and slow down as well. So yeah, ultimately what's produced, of course, is the time it takes to traverse it, because this is a sort of discrete simulation, so it needs to have a calendar of how things work. But yeah, how that gets determined is flexible.
Perfect. I don't see any other questions. So
I suppose my last thing, again, this is sort of an open, very much an open project. The code should be there, and in the spirit of open, please go check out the GitHub, and feel free to sign up and comment and contribute where needed.
Yes, since we have 1 more minute, I think there's one last question. Can the proposed model generate good quality timetables with minimum passenger delay?
So I guess if the question is about optimization, that would have to be sort of a separate process. So you could optimize over the model and try different things, or even run the model a couple steps, look at the state, try to optimize, change the behavior, optimize again. Right now, I know I can produce what the schedule is suggesting, and then muck around with the schedule a little bit, add some situations as well.
Yeah, I think it's a test bed. It's a test ground really for testing different schedules or different network configurations, different services.
And certainly, as if use cases come up that are very specific, that are very, very interesting, like being able to produce a schedule after you've played around with things, or those kinds of use cases, then we should have a conversation about that for sure too.
Perfect. Okay, so thank you everyone. It's exactly 12 now, so we reached the end of this session. I thank